Welcome. In today's video, we are going to discuss how to derive the probability generating function for the discrete uniform distribution. So let's begin. Suppose X has a discrete uniform distribution with parameters A and B, where A is the minimum and B is the maximum. The probability mass function, or the PMF, of X is therefore given by the following. Px of X is equal to 1 on B minus A plus 1, where X takes the values A plus 1, all the way to B. Now, using the definition of the probability generating function, we can say the PGF of X is, apologies for the notation, capital PX of Z, as opposed to lowercase p, although it might be hard to tell with the PMF, which by definition is the expected value of Z to the power of X, which by definition of expectation of a function, if you recall, in general, the expectation of some function of X, let's say f of X, is equal to, at least in the discrete case, the sum of X in its support of the function of X multiplied by the probability mass function. That's the general definition for expectation. So applying that general definition of expectation to our values here, that gives us Z to the X times P, the probability mass function, where X is an element of the support of X. Now, of course, we know what our support is. It's the values from X equals A to X equals B. So we can rewrite that summation as X equals A to B. We've still got Z to the X times, and we've of course got our 1 on B minus A plus 1 as our probability mass function from above. Now, one thing to note is that the index of summation is dependent on X. The Z to the X is of course dependent on X, but the 1 over B minus A plus 1 is a constant with respect to X. And so because we're summing across a constant multiplied by a function, that constant can actually be taken outside the summation. So we can rewrite this as 1 on B minus A plus 1, sum of X equals A to B of Z to the X. Now, in our next part, we know here we're actually summing in part a geometric sequence, right? A geometric sequence. Z to the X is a geometric sequence. Now, we know from previous mathematical studies that in general, when I have a geometric sequence which has the form of AR to the N, and I sum that sequence, or maybe I should say not AR to the N, but rather AR to the let's say X, from X is equal to 0 to N minus 1. In other words, I've got A plus AR plus AR squared plus all the way to AR to the N minus 1. We know from our studies of geometric sequences, specifically the study of geometric sequences, or the sum of geometric sequences, sorry, that this has the form a times 1 minus r to the n all over 1 minus r. Now, in the case of our geometric sequence here, we notice that we're summing not from the terminal 0, but rather the terminal a. And obviously don't get confused between the a here and the a here. This is rather just a constant. This is the beginning terminal. Now, noticing that, keep in mind that we can express this sum as the difference of two other sums. Let me write that difference down and then just explain it further. So I'm going to write it for you here. X equals 0 to b, z to the x, minus the sum of x equals 0 to a minus 1, z to the x. So in this next step, what I've done to try and make it look like this form over here is I've rewritten the sum from x equals a to x equals b as the difference of two individual sums here. One going from x equals 0 to x equals b, and then I'm subtracting all the x equals 0 to a minus 1s. By doing that, effectively, I'm just leaving the components when x equals a and to x equals b. And then now I can apply my formula here for the sum of geometric sequences. So in this particular instance, we've just got z to the x. So it's just the r to the x component. The a, of course, in this particular example is just a coefficient of 1. So we can just almost ignore the a's and go straight to this, just the 1 minus r to the n over 1 minus r. In this case, of course, we don't have r, but we have z. So keeping that in mind, we've got b minus a plus 1. We'll use the formula exactly. So our a value is 1. And then we've got times 1 minus z. Apologies. Z to the power of. Now, careful here because the terminal is b. In our example, the terminal is n minus 1. So if b is our n minus 1, that means that our n value, right, if b is equivalent to the n minus 1, that means our n value is equivalent to b plus 1. So the coefficient here must be b plus 1. And then, of course, we have divided by 1 minus z. Equivalently, we've also got the second part of that sequence, which is going from 0 to a minus 1. And going from 0 to a minus 1 leaves 1 times, and again, we can use our geometric formula expression. A in this case is 1. We've got a 1 minus r to the n. 1 minus, it's now z. Now notice here in our expression we had an n minus 1. We have an a minus 1. We get an n in the expression. Therefore, we get an a in the expression here. And we divide that by 1 minus z. And surely enough, we can now simplify this a little bit. So this becomes 1 on b minus a plus 1 of 1 minus z b plus 1 over 1 minus z minus 1 minus za over 1 minus z. And of course, luckily enough, these two terms have the same denominator, so we can just add the numerators together. And doing that, we get a minus 1 here will cancel with the positive 1 at the front, and a minus negative z to the a will give us a positive z to the a. So overall, we get 1 on b plus a minus 1 z to the a minus z to the b plus 1 all over 1 minus z. And of course, sometimes instead of putting this as a separate fraction at the front, we can write that as b minus a plus 1 in the numerator. Sorry, in the denominator. And there you have it. We have derived the probability generating function for the discrete uniform distribution. Now, of course, we could theoretically compute the moments of the distribution by using our understanding of moments or our properties of moments, and in particular recall the following two expressions, that the expected value of x minus 1, x minus 2, ... x minus n plus 1, we could compute that by taking px of n evaluated at 1. But do keep in mind that for this particular expression here, it actually gets quite complicated. And so I'm not going to go through a full derivation of how we can get the expected value in this particular video, because you'll notice, and it's one of the unfortunate properties of this, if you do plug in a value of 1 into this expression, you get a denominator which is 0, and you get a numerator which is also 0. And even when you do compute, say, the first derivative and the second derivative of this particular function to evaluate the moments, the first moment and the second moment, you'll find that the numerator and the denominator are both at 0 when it equals 1. That actually forces you potentially to use L'Hopital's rule in order to evaluate the expected value. In saying that, it therefore is actually less convenient to use the probability generating function to evaluate the moments. And so typically we wouldn't do that for the discrete uniform distribution. Nonetheless, we have derived at the very least the respective probability generating function. I hope this video was useful. Thanks for watching. Hope to see you in the next one.